I see. Okay. Can you close that?
Okay. Okay. Well, good afternoon or good morning, everybody. It's a cool day here in Boston. It's about low 40-degree Fahrenheit. I suspect it's a lot colder than it is in Hawaii right now, and maybe comparable or plus or minus a little bit of what it is in Alaska. So hope you're having a good day. Welcome back for those who are here. Hopefully a few more will be joining us. Send me a chat if you have any questions. There was one question that came up at the very end of the session last week, and Patrick sent it. A question about degrees of freedom, and I've added a few slides towards the end of today, and I'll hope to address that question and give you at least one answer to it when we get to it. So, Patrick, hold on, and we'll hopefully get to your question at the end. But what I want to do today is this is the fourth of our, I guess, 5 sessions on regression, and I'd like to wrap up and say a few last words about logistic regression models, and then hopefully introduce the concept of a linear regression model. So to do that, let me pick up where we left off last week, and what I was using as an example some data from the Framingham Heart Study. And remember what the data set involved was about 1,300 people who were being followed for almost 20 years to see who was developing coronary heart disease or not. So the outcome of interest in all the analyses we've done so far has been this variable new CHD. Coded as 1 if you developed coronary heart disease during 18 years of follow-up, and 0 if you didn't. And what we're looking at is models that predict the risk of developing coronary heart disease. So the model was giving everybody a risk, P, for that person's risk of developing coronary heart disease. One of the things we want to talk about today is how do we judge whether this model is fitting the data set well? How do we judge which of a couple of different models might be the better model to make our final results from? Last week we were looking at the relationship between gender and the risk of developing coronary heart disease, asking if men are more likely to develop coronary heart disease than women. Today we're going to talk about a little bit more about smoking. We're going to look at smoking in a couple of different ways. The original data set was called SIG, C-I-G, which was the actual number of cigarettes a person was smoking at the baseline exam. 0 if you're a non-smoker, 1, 2, 3. I think the maximum was 60. One of the things we did last week is we broke that into a PAX variable, which categorized that cigarette variable into 0, 1, 2, or 3. 0 for non-smokers. 1 pack meant anybody who's smoking anywhere from 1 cigarette up to and including 20 cigarettes a day. 2 packs are 21 to 40. 3 packs are 41 to 60. One of the things we hope to see today is a collapsed version of PAX, which is a variable called smoke. It's 1 if you smoke any amount of cigarettes, 1 or more cigarettes a day, 1 or more packs a day. It's 0 if you're a non-smoker. But last week we also, and the week before, we also looked at a series of indicator variables, indicating which amount of smoking you performed in terms of packs per day. Pax 1 was an indicator variable, which was 1 if you smoked 1 pack a day, 0 if you didn't. Pax 2 is if you smoked exactly 2 packs a day, 0 if you didn't. And Pax 3 if you smoked 3 packs a day, 0 if you didn't. And later on today, we're going to be looking at some other variables. The person's blood pressure, a continuous variable measured in millimeters of mercury on the systolic scale. SBP2 is going to be the square of that variable, the person's blood pressure multiplied by itself. So if you have a blood pressure of 140, your value for SBP2 is 140 times 140, whatever that means. SBP10 is the blood pressure at the 10th follow-up exam, 18 years after the study began. That's going to be an outcome we're considering the end of today and next week when we deal with linear regression. And cholesterol is the continuous value of the cholesterol values of these people at baseline. So we're going to be using SBP, SBP2, and cholesterol as confounding factors we want to control for with these models as we go through today. We'll use SBP10 later on today as an outcome variable, measuring the person's blood pressure 18 years after the study began. Okay. So if you remember where we left off on last week, is we were talking about how do you control for confounding factors, a single confounding factor, and we talked about controlling for age as a binary variable last week, above and below age 55. We also talked about controlling for smoking, and just to pick up where we left, if you have a continuous confounder like age, or in this case, cigarette smoking, there's a couple of different ways you can control for it in a model. We can categorize that continuous variable into categories like tax 1, tax 2, tax 3, for the different levels of smoking if we categorize smoking into tax. Or we could keep cigarettes as a continuous variable and include it in the model not as a series of indicator variables to represent different categories, but as a one or more variables to represent a continuous relationship that confounder might have to the outcome. So for example, here are two models I want you to consider for models that might control for smoking. Let's suppose, again, we want to pick up where we did last week. We want to know whether sex, male, is related to your risk of developing coronary heart disease, P, during 18 years of follow-up. And male, remember, is coded 1 if you're a male and 0 if you're a female. Now we want to control for smoking. The way we're going to do it now is we're going to control for smoking as a categorical version of cigarettes. We're going to take the variable PAX, coded as 0, 1, 2, and 3. We're going to break it in, we're going to assign people into those categories. Essentially what this is stratification. Let's put people into cigarette categories and look at the effect of male versus female within each of those categories, and then average those comparisons across all levels of smoking. So I mentioned before that if you have a categorical variable, say PAX, which has 4 values to it, 4 levels, 0, 1, 2, and 3, we need 3 indicator variables to represent those 4 values. And that's what I have in this model. A variable called PAX1, PAX2, PAX3 to represent 3 of the 4 levels of PAX. You don't need the 4th level because if you're a 0 on PAX1, a 0 on PAX2, you're a 0 on PAX3, by definition you have to be a non-smoker, the other category, which we do not have an indicator variable in this analysis. The question is, if we fit this model, what set of assumptions are we making, and is fitting the model this way better than fitting it other ways? Would it be better to include cigarettes as a continuous variable? So let's just go through the output we get if we fit this model. This is what we have on the rest of this slide on the next. This is SAS output from fitting the model with gender and smoking, smoking represented by 3 indicator variables to represent the 4 categories of PAX. And I'm going to be drawing your attention to a couple of output pieces like we've been doing all along. We have this line -2 log L. Remember what L is the likelihood. It's the probability of observing that which actually happens. Now we have 1,363 people in this data set. 100 or so of them developed coronary heart disease. The other 1,200 didn't. So what the likelihood is going to look at is the probability of developing heart disease for all those people who developed heart disease, and the probability of not developing heart disease for all those people who didn't. So what we're going to be doing is we're going to be writing down an expression. Our likelihood L is going to equal a bunch of P's times 1 minus P's times 1 minus P's times P's, etc. It's going to be a probability of observing what actually happened to people. For everybody who developed heart disease, we're going to put a P into this expression. For everybody who didn't develop heart disease, we're going to put a 1 minus P. What we want is the probability of what actually happened to each of these 1,363 people. Now, a good fitting model, if you think about it, will be a model that gives high risk of getting heart disease for those people who actually got heart disease, and low risk of getting heart disease for everybody who did not get heart disease. Meaning, think about it, what we have is a P for everybody, a risk of getting heart disease. And a good fitting model means that the P's will be close to 1 for people who got heart disease. The P's will be close to 0s for people who didn't get heart disease. That would be a good fitting model that gives probabilities that reflect what actually happened to people. Well, think of this likelihood expression here, this L. Fix that value. So it's capital L. This likelihood, hopefully, the P's will be close to 1 for people who got heart disease. The 1 not get heart heart disease because we want the P's for those people to be close to zeros. Someone who didn't get